This is an example problem showing how to find the electric field in a point due to several point charges. Also how to find the force on a point charge due to other point charges. And finally, how to use symmetry or to tell if you can use symmetry in order to simplify the problem. Okay, in this problem, we have a 5 microcoulomb charge that is kind of in the middle of all of these other point charges, arranged as shown in the diagram. And first, we're supposed to find the electric field at the point where the 5 microcoulomb charge is due to the other 4 charges. Well, whenever you want to find the electric field at a point due to several different charges, the way to do that is to find the electric field at that point due to each individual charge and add them all up. In other words, if we want to find the total electric field at a point, then what we should do is find the electric field at that point due to the first charge plus the electric field at that point due to the second charge, third charge, and fourth charge, etc. And you can add as many terms as you need, but in this particular example, there are 4 charges that are going to affect the electric field at this central charge right here. Okay, notice that I do not have a term for the electric field due to that 5 microcoulomb charge itself. Charges do not experience their own electric fields. So when we're trying to find the electric field at that spot, we don't have to include the charge that's at that spot. Okay, so what we need to do is find the electric field due to each of these 4 other charges at that point where the 5 microcoulomb charge is. Okay, now first let's see if it's possible for us to use symmetry in order to simplify the situation. Okay, whenever you've got several charges, sometimes the electric field from 2 or more of those charges will cancel each other out, and you don't have to calculate their contribution. So let's see if we can find any charges like that here. The key to look for symmetry is to see, are there any charges that are the same distance away but 180 degrees apart? Okay, and you also want them to have the same charge. So there are 2 charges that fit that criterion, this one and this one. These 2 charges are the same distance away from the point in question, 20 centimeters. They both have a 3 microcoulomb charge, and they're located 180 degrees apart from one another. The one on the right is going to have an electric field at the 5 microcoulomb charge that pushes it this way, and the one on the left is going to have an electric field there that pushes it that way. And because they're the same distance from the point in question, and they both have the same charge, 3 microcoulombs, their electric fields will cancel each other out, and we don't have to worry about them. Okay, so you can say, hey, these 2 terms, the electric field due to charges 3 and 4, they're going to cancel, and we don't have to worry about them. So we've just cut our work in half. Right now we only have 2 charges that we need to find the electric field for. Now, can we use symmetry with them? No, unfortunately not. For 2 reasons. One, they're not 180 degrees apart. One of them, the electric field due to the 1 to charge number 1 is going to be this way, and charge number 2, since it's negative, its electric field will be that way. Okay, and they're not going to be the same size either, because one of them is a negative 10 microcoulomb charge and the other one is a 4 microcoulomb charge. So we can't use symmetry on charges 1 and 2. We can use symmetry on 3 and 4, though, so that cuts our work in half. So what we need to do is find the electric field due to charge 1 and the electric field due to charge 2 and add them up. And we'll have to add them up as vectors because electric field is a vector. So first, let's find the electric field due to charge 1. And we're just going to go with magnitude first. Okay, find the magnitude, and we'll find the direction separately in a moment. Okay, now, in general, the electric field, the magnitude of an electric field due to a point charge is equal to K, where K is Coulomb's constant, times Q, where Q is the magnitude of that point charge, over R squared, where R is the distance between the point charge and the point where you're trying to find the electric field. So we can use that to find the electric field at the 5 microcoulomb charge due to charge number 1, the 4 microcoulomb charge up top. Okay. Now the Coulomb constant, K, is 8.99 times 10 to the 9, and that's in units of Newton meters squared per Coulomb squared. Okay, so there's K. Q. Q in this case is charge number 1. It's 4 microcoulombs. Now I need to write that instead of in microcoulombs. I need to convert that to coulombs. So that's going to be 4 times 10 to the minus 6 coulombs. And then we need to divide by the distance between charge 1 and charge 5, where we're trying to find the electric field. Well, I don't have that distance written in the diagram, so we're going to have to figure it out. Right? So we have this distance here is marked as 20 centimeters. This distance is also marked as 20 centimeters. So if I want to find this distance, the hypotenuse of that triangle, I can use the Pythagorean theorem, right, where this distance is A, this distance is B, and this distance is C. Since A squared plus B squared equals C squared, and it's also true that C is equal to the square root of A squared plus B squared. Converting from centimeters to meters, I have 0.2 meters squared for side A and 0.2 meters squared for side B. Okay, when you square those, add them, and take the square root, you get that side C is equal to the square root of 0.08 meters squared, or that works out to be 0.2828 meters. I'm going to keep extra digits throughout this calculation. Okay, I'm going to keep 4 digits in all of my calculations, and then we can round off at the end. Okay, but if you round off too soon, you're likely to have a round off error at the end. So we'll just keep some extra digits in the intermediate part of this calculation. Okay, so there is our distance R. So we'll plug that into our equation down here. R is 0.2828 meters squared, which will be 0.08 meters squared, by the way. So if you multiply all of that out, then we get that the magnitude of the electric field due to charge number 1 is 4.495 times 10 to the 5th newtons per coulomb. Because the coulombs here cancels one of these coulombs. We have meters squared there canceling meters squared there, and you're left with newtons per coulomb. It's for the direction of the electric field due to charge 1. We're going to need to find the x and y components. So we need E1x and E1y. So we need to resolve that the vector E1 into its x and y components. Right, so put your attention up on the diagram for a moment. If the electric field E1 is this way, okay, and we know that it's that way because this is a positive charge here, okay, and the direction of the electric field points by definition in the direction of the force that would be experienced by a positive charge. So if I put another positive charge down here at the tip, it would be repelled by the 4 microcoulomb charge. So its electric field points along the direction of that green line I just drew. Okay, so I need to find the electric field component in the x direction and the electric field component in the y direction too. So this component will be E1y, and this component here, E1x. Okay. Now, in order to find those, we need to use some trigonometry, and we'll need to find the angle. Well, fortunately, since both sides of this similar triangle are 20 centimeters, and 20 centimeters and 20 centimeters, we know that this is a 45, 45, 90 triangle. So here, here's the right angle. We've got a 45-degree angle here and a 45-degree angle here. So we can use trigonometry and the 45-degree angle in order to find E1x and E1y. Okay, E1x, since it's adjacent to the hypotenuse of that triangle, will be equal to 4.495. That's the total electric field. Times 10 to the 5 newtons per coulomb. Since it's adjacent, we'll use cosine 45 degrees. And then E1y is equal to the total electric field E1 times 10 to the 5 newtons per coulomb times the sine of 45 degrees because it is opposite to the 45-degree angle. Sine 45 degrees and cosine 45 degrees happen to be equal to each other. So both of these, the x component and the y component, turn out to be 3.178 times 10 to the 5 newtons per coulomb. It's important that we pay attention to the direction here. All we've found so far is the magnitude of the x and y components of E1. To get the direction, we need to use what we know about how electric fields point. Okay, electric fields point in the direction of the force that would be experienced by a positive test charge. So, since I have a positive charge here, and I'm looking for the electric field down here, I imagine putting a positive charge down here where the 5 microcoulomb charge is, and I see what direction would the force on that charge be due to the charge that's up here. Of course, 2 positive charges are going to repel, so the direction of the electric field would be down and to the right. Since it's down, we know that the y component is going to be negative. Since it's to the right, we know that the x component is going to be positive. So we've now found the x and y components of the electric field due to charge 1. We need to do the same thing for charge 2, and since we're about to run out of room, I'm going to clear some of these things, and then we'll do the electric field due to charge 2. Okay, so we've got the x and y components of the electric field due to charge 1 written up here in the upper right corner now. And we're going to find the electric field at the point in question due to charge 2. So again, we'll use k times the absolute value of the charge over the radius squared, or the distance between the point and the charge, squared. K is 8.99 Newton meters squared per Coulomb squared. We have minus 10 times 10 to the minus 6 coulombs, absolute value, over the distance. This time the distance is this distance here between charge 2 and charge 5, but all the distances involved are exactly the same as the distances involved between charge 1 and charge 5. So we can use the same R that we found before, which was 0.2828 meters. So put that there. Once you multiply all of those things out, put them in your calculator, you get that the magnitude of the electric field due to charge 2 is 1.123 times 10 to the 6 newtons per coulomb. Just as before, we need to find the x and y components of that electric field. Also, just as before, we have a 45-45-90 triangle, so the trigonometry is the same, the angle is the same, the only thing that's different is the hypotenuse. Okay, so we have E2x is equal to E2, which is 1, 2, 3, there's 10 to the 6 newtons per coulomb, times the cosine of 45 degrees. Multiplying that out gives us 7.946 times 10 to the 5th newtons per coulomb. E2y is the same number, 1.123 times 10 to the 6 newtons per coulomb times the sine of 45 degrees. Since sine and cosine of 45 degrees are both the same, we end up with the same answer. Okay, now let's pay attention to the direction again. I have a negative charge down here. It is a negative 10 microcoulombs. So what direction would the force be? If I had a positive charge up here where charge 5 is, it would be down and to the left along that line. Down and to the left means that I have a negative x component because it's to the left, and I also have a negative y component because it's down. All right, we're almost finished. You can see the end from here. Now that we have the x and y components of all of the individual electric fields, we can find the total electric field by adding up x components and the y components. The total electric field's x component is E1x plus E2x. Right? E1x is a positive 3.178 times 10 to the 5th newtons per coulomb. E2x is a negative 7.946 times 10 to the 5th newtons per coulomb, meaning that when you add those up, you get a negative 4.7 8 times 10 to the 5th newtons per coulomb. Okay, or 4.768 times 10 to the 5th newtons per coulomb in the negative x direction or to the left. Okay, we need to clear some more space, so I will do that. We have cleared some space and shifted what's left up a little bit so that we can continue working down at the bottom of the page. Okay, so what we found is the x component of the total electric field. Now let's find the y component of the total electric field. ETY is E1y plus E2y. E1y is a negative 3.178 times 10 to the 5th newtons per coulomb. E2y is a negative 7.946 times 10 to the 5th newtons per coulomb. So the total y component is negative 1.112 times 10 to the 6th newtons per coulomb, or 1.112 times 10 to the 6th newtons per coulomb in the negative y direction. We're finally ready to find the magnitude of the total electric field. The magnitude of the total electric field will just be using the Pythagorean theorem for the total x component and the total y component of the electric field. Since the total electric field is the hypotenuse of the triangle that's made with ETX and ETY. When you plug those two numbers in, square them, add them up, you end up with the square root of 1.464 times 10 to the 12. And then when you take the square root of that number, you get 1.211 times 10 to the 6 newtons per coulomb. And that is part of our final answer for part A, although we still need to find the direction. Let's clear some of the stuff that we don't need anymore and move what we do need up into the corner where we can keep it Okay, so now all we have left is the direction. Let's draw our triangle that we have. So we have ETX is minus 4.768 times 10 to the 5th. So that's going to be a vector in the negative x direction. 4.768 times 10 to the 5th newtons per coulomb in the negative x direction. And in the y direction, we have something that is about 3 times bigger than that, 1.112 times 10 to the 6th. So we draw a vector that's about 3 times longer. Okay, this is 1.112 times 10 to the 6th newtons per coulomb down. So the net electric field, or the total electric field, is going to point down this way. And let's find the angle that that vector makes with the horizontal. Okay. The x component is adjacent to it, and the y component is opposite to it, so we can use inverse tangent. Okay. Inverse tangent of opposite, which is 1.112 times 10 to the 6th newtons per coulomb, over 4.768 times 10 to the 5th newtons per coulomb. Okay, the units cancel. So we get that this angle, theta, that the electric field makes with the horizontal is about 66.8 degrees with respect to the horizontal. So we're finished with part A. We've found the total electric field at the 5 microcoulomb charge due to the other 4 charges. Now, you might think we're only half done because we still have part B to go. But in fact, we're almost finished. Now that we've done part A, part B is really easy. Because in order to find the net force on the 5 microcoulomb charge, we can use the electric field that we've already found. Because once you know the electric field at a point, the force on a charge at that point is just equal to the electric field times the value of that charge. And that's a vector equation, which means that if I take the electric field that we just found, 1.211 times 10 to the 6th newtons per coulomb, and I multiply it by the charge Q that's at that point, which is a 5 microcoulomb charge, 5 times 10 to the minus 6 coulombs. Then we have the answer. .055 newtons. And the direction is exactly the same as it was before, 66.8 degrees, because this is a vector equation. So that's all. Part B is easy once you've done the work in Part A.